Yes, I can kick in with a different presentation that is again about covariance neural networks. So connection is pretty clear, but it's more from a methodological perspective and tries to deal with slightly different settings. So hopefully it's not too repetitive. This was work that I did with Elvin and then Ayushman and Sandeep from the Indian Institute of Science. And okay, the motivation is very similar. The only difference that I will highlight is that I'm not only focused on brain applications, that figure you're already familiar with, but I also looked into other ways that covariance information might be useful in data, because it's actually very common for practitioners to use covariance related information in a variety of applications, right? So you can think of financial data where you have people look at correlations among different, the prices of different assets. And they're usually, I mean, correlations are meaningful because you have that different factors affect multiple assets in the market instead of a single one. So looking at correlations might identify these shared behaviors. Or for example, this wearable sensors application where people place sensors at different locations of their body and then they perform some activities like running or biking or jumping. And for example, what you might want to do is try to classify the action that the person is doing. And of course, different areas of the body are moving in a coordinated way to perform some actions. So correlations are relevant also in this case. So yeah, we can capture this kind of latent interactions among the data points using the covariance matrix. And one way that you could do that is via the principal component analysis. So again, the composition of the covariance and projection of the data into these directions that maximize the variance of the data. You can use this for dimensionality reduction, which you can see also as a filtering operation, where this kind of plot shows the eigenvalues here on the x-axis. And basically what PCA does when you want to select, let's say, the first two components is it applies this sort of high-pass filter where you are zeroing out all the lower eigenvalues and keeping only the largest ones. Or you can use covariance filters to leverage covariance information. Again, Sora introduced them very well before. So very briefly, you build a graph with the covariance matrix and your features become graph signals. So in that case, in Sorab's case, it was cortical thickness measures, but it can be, I don't know, the altitude of a sensor on your wrist or your elbow, for example. Right? You can do a convolutional filtering on this graph, where same figure as before, where you shift a signal from a node to its neighbors, taking powers of the covariance matrix. And then you aggregate everything together by multiplying with these learnable coefficients h and summing all of this. And once you have the filter, you can build a neural network by having a filter banks. So many filters acting in parallel, adding a nonlinearity sigma, which increases the expressivity of the model, and stacking multiple layers on top of each other. This has a connection with PCA that we already know. So yeah, the only thing I will highlight is this plot here, where you can compare that PCA is basically learning just this fixed high-pass filter, whereas basically this VNN can learn any function in the spectral domain. So this H is this kind of HK times lambda power K. So it's a polynomial, but you can play around with it, and by setting different Ks, then you can learn different shapes here. So it's a more flexible approach than PCA. It's data driven, and of course, I mean, you can show that this for some choices of H retrieves the PCA transform. Now I'll get to the new point compared to what we already knew, which is what if we have outliers, right? So it's very common in many data that the observations are not reliable. We might have outliers, or we might have missing values. So it can be that a sensor placed somewhere on your body gives a completely wrong measurement, or we lose the communication for some recordings, right? So we just don't have that value. And the problem with this setting is that the principal components or the covariance matrix can be very largely affected very quickly. So in this toy example, I have 100 data samples and 5 outliers. And the principal directions, the red ones, are completely off compared to the true ones, right? The true ones are the green, which, okay, they were very well retrieved, but I just add 5 outliers and everything goes wrong. So in this setting, you can't really trust either PCA or VNNs because they act on the sample covariance matrix. And if your data contains a few outliers or missing values, the sample covariance is not reliable anymore. So we want to solve these issues. And basically, we want to propose this model, these robust covariance neural networks, to achieve these 3 main desiderata. So we want to use covariances for data processing because there is clear evidence from the literature that covariances are useful to model interactions among data, and we want to do it in a learnable way because it's more flexible and more expressive. But we want to be robust to outliers and missing values in a way that depends also on downstream tasks. So we want to kind of learn this correction for the outliers. And we also want to achieve the stability to the finite sample estimations that Saurabh mentioned before. I will briefly touch upon that later. So this is how this model works. We take the perturbation model inspired by robust PCA, where we assume that our observed matrix, data matrix X, is the sum of 2 different matrices. One is a low-rank matrix, which we call L, and one is a sparse matrix S. L encode the real data. So we assume that the real data lies in this low-rank space. And the matrix S encodes the perturbations, so either the outliers or the missing values, right? So missing values would just be the inverse, the negative of that value, right, to zero it out. And if we look at what the covariance looks like for this model, we just take this, we just compute it, right? And then we end up with this expression where LL transpose is the true covariance that we would like to work with. And these terms here are the perturbations due to the outliers. So basically we have one term, this red one, which is low rank because the rank is dominated by this L, right? And one SS transpose, which is sparse. So basically we can assume that our observed covariance, the sample covariance, C hat here. Yeah, this is wrong. So this would be the C, the true covariance C. So yeah, I used the wrong notation, but then it's the observed, it's the true one plus a sparse perturbation error plus low rank perturbation error. And then we use this into our VNN. So VNN allows us to have the flexible processing of covariance information and to correct for this outliers setting, we change the training objective of VNNs to the following. So we have a term of the final downstream loss that depends on a task. We have a training dataset with observations X and labels Y, which can be, for example, the age of a patient, or it can be the action that a person is performing. But instead of feeding the model with just the covariance matrix, the sample covariance, we feed it with all of this, right? So we have the sample covariance plus these 2 correction terms that we are trying to estimate to compensate for the outliers. And then we have a term in the loss that promotes sparsity for the ES. So this matrix that should be sparse, and a term that promotes the low rank structure for EL. So in this way, we train this end to end on a training dataset. So in this case, we hope to basically get all the benefits of VNNs, but also compensating for outliers, missing values, and noise in the data. We can have some theoretical analysis of this model by looking at what kind of perturbations does this covariance matrix that we are using face. And in particular, we have 2. There is one perturbation due to the outliers, which is what I discussed before. So we model it as one low rank term, one sparse term. But then there is also the usual instability, the usual perturbation due to finite data settings, because in practice, we always estimate the covariance matrix from a finite number of observations. And based on how many are these observations and how large is the dimensionality of the data. This estimate can be good or bad, right? And then we want to see how this model behaves based on how good is this estimate. And we find this bound. So here what I'm comparing is I take the VNN, or in this case just a filter, but then can be extended to the whole VNN on my, let's say, sample covariance plus the correction terms. And I compare the embeddings of this model to the embeddings of the same filters of fixed coefficients H, but applied on the true covariance matrix, which I don't know. So this is an ideal bound, right? But this also tells you how good you can perform in practice, given that you will never be in this setting because you don't know the true covariance matrix of the data. And we can find a bound for this quantity that looks like this. And yeah, I just want to highlight that there is one term that depends on the inverse square root of the number of samples, which is what we also observe for the nominal VNNs. So the more samples you observe, the better your covariance estimate, right? So the lower the instability, right? So the closer you get to the ideal case. So what's interesting in this case is that we have a dependency on the number of samples that allows us to say, okay, based on how many samples we observe, this is how good our performance will be compared to the ideal case. And then we have an additional term, which doesn't appear for the nominal VNN, which is how good can we reconstruct the true covariance matrix, right? So we assume this model, right, where we have our sample covariance plus two terms. Is this the true model, right? Is it reliable? Does it work? This term delta encodes how good this reconstruction is. And there are some proofs that show that under some assumptions on the data structure, of course, this model can reconstruct the true data matrix and therefore the true covariance. But then, of course, our training is a bit more, there is a part of the training that depends on the downstream task, right? So that can either help, because in some cases the downstream task can provide you useful prior towards reconstructing the correct data matrix, even if the assumptions are not perfectly met. But then on the other hand, the downstream task can just pull away from your reconstruction objective, and then you're just reconstructing a different matrix. And we will see that in experiments as well. So as for experiments, I have some synthetic results where first I generate a regression task, and I change this. So I set some values to 0. I have my data matrix, right? I generate my regression tasks, and then I set some observations of this data matrix to 0. And I do this for increasing percentage of missing values. And I see how the performance of different models changes. We have, so VNNC is the clean data, the covariance VNN on the clean data. VNNP is the VNN on the perturbed data, so when I remove the values. RPCA is, I take my perturbed data matrix, reconstruct it with a robust PCA, and then use a VNN, so it's a decoupled approach. And these two VNNs are this joint approach where we are training everything end to end. And these are more or less the behaviors. Here I have the regression performance, the mean squared error on the regression task, and this is instead how good is the reconstruction of the covariance. So this is the error in reconstructing the covariance. So basically what we see here is that up to some point, let's say 0.05, the VNNs, the RVNNs are matching the performance of the VNN on the clean data, or even improving it. And then okay, if the missing values increase, then okay, the performance goes a bit off. But what's interesting here is that at this yellow curve, right? So here the performance is even improved compared to the clean data. But if you look here, the reconstruction of the covariance is very large. There's a lot of errors. So basically what the model is doing here is it's learning a different graph, right? It's not even learning the covariance that we were expecting. So you can play around with the hyperparameters that tell you how much focus you want to put on the low rank and the sparsity of your correction terms to kind of achieve either a good reconstruction performance if you care about it. So here the green line is achieving basically the same reconstruction results as our robust PCA, Or if you care more about performance, then you can give a bit less importance to that and focus more on performance alone. On real data, I used two datasets here. One is brain recordings for an epileptic seizure. And I'm trying to classify whether the sample was recorded before or after the seizure. And the second dataset is these motion sensor recordings of the human body. And I'm trying to classify what action a person is performing. And I increased the missing values as well. And basically on these datasets, well, on both, the RVNN is the least affected model by the increasing of missing values, right? So here it decays slower than for the baselines, and yeah, the dataset is not even affected by missing values. So this kind of corroborates that this framework is able to maintain performance over a variety of missing rates, basically. So yeah, I can sum up the presentation where we are dealing with covariance information in general, and we observe that since many data sets contain outliers or missing values, right, and this can affect the covariance estimations largely and make traditional data processing and machine learning techniques unreliable. So, for example, PCA. And to counteract this, we proposed robust covariance neural networks, where we used these correction terms for the covariance matrix, a sparse one and a low rank one, inspired by the robust PCA model. We showed that this kind of framework is stable to find sample estimation errors, so it maintains the stability related to the error of I only have a limited amount of samples to estimate my covariance, and there is an additional term that depends on how good I am to compensate for the outliers. And also experimentally, we showed that this framework is able to maintain the performance of basically the advantages of VNNs, even when there are missing values. And doing this joint approach end-to-end works better than first reconstructing the covariance and then applying a VNN. So there is an advantage on this joint estimation. So yeah, that's the end. Thank you for listening.